Hello and welcome to your Regularization Python lecture. So the first thing that I'm going to do, of course, is going to be to run all my packages. And the next thing I'm going to do is load all of my data. So this data set is super fun, and it is courtesy of the wonderful Julia Silge, who provides the code to scrape this data on her website that I have linked here. So what we have here is a data set about this show, The Office, and it has a bunch of information, but if I scroll over, the thing that we're going to be interested in today is predicting what is the rating of the episode of The Office on IMDb. And we have a bunch of different variables here. We have, well, something we're not going to use is the episode name, but we have the season, we have the episode, and then we have the count of times that each character talks. So you can see here, for instance, in season 1, episode 1, Dwight speaks 29 times, Jim speaks 35 times, etc., for everyone. And then we also have Boolean values, zeros or ones, for which producers were a part of making the show, or like the episode of the show that we're looking at. And we want to use these variables to predict what is the IMDb rating for this show. So I'm loading in just a different form of the data set. It's pretty much the same. It just works easier for ggplot. If you're interested, you can go and look. But let's just really quickly explore this data. So I'm going to say ggplot office long. So let's plot name. So this is the name of the person. And then y equals value. This is the number of times they spoke per episode. And we'll make it a little pretty. We'll say fill equals name, and then plus g on box plot. Okay, and so when we run this, we should get a beautiful rainbow graph that shows us across all episodes of all different seasons of The Office the range of number of times that each individual person talked. So for instance, the clear one that stands out, at least in this one, is Michael Scott. And Michael Scott has a huge range of number of times that he's talked. And that's probably because he wasn't in the final seasons, but he's a main character for every season that he's in. So you can see that often he's talking a lot, but there's occasions when he talks not at all, probably because he's not in the episode. Another interesting one that I saw here was Jan. If you've watched The Office, Jan is a character where when she's in an episode, she's usually part of the main storyline, but she's not in every episode. And that probably explains the pattern we see here, where for most episodes, she has 0 lines, but when she is in an episode, she has quite a few, which we can see in all the outliers that are coming out of this box plot here. For other different characters, probably as you expected, for instance, it's Pam. So she talks a lot, sometimes a little bit, but she generally has more lines than most people. You can see Jim here and Dwight here. So even if you just look across this plot, you can see, well, clearly Jim, Dwight, Pam, and Michael are some of the most main characters, at least that are consistent throughout this series. We could spend hours and hours talking about this. Obviously, I love The Office and I think it's really interesting, but let's move on for now. So I'm going to grab the columns, basically all the numeric columns from our data set. I'm just going to grab their names and store them in the variable feat, and then I'm going to grab my x values and then the y values. So here I'm predicting the IMDb rating, so I'm going to grab those here. And then I'm going to do a train test split just for ease of showing you. I've seen a lot of people when you're justifying your validate your model validation method of saying like, well, we used it in class. That's totally fine, but you should be thinking about your actual data set when you're doing your homework. The only reason that I'm doing train test split here is because we have a limited amount of time in this lecture. So when you're actually doing your validation, think about your data set a little bit more. Okay. So I'm going to run this. Actually, before I run this, let's add some more things. So remember with Lasso and Ridge, it's important that you're standardizing your variables before you put them in. Because when you think about the loss functions that we talked about in the last lecture, those aren't really accounting for the scale of the variables. Lasso and Ridge just say, oh, if the coefficients are big, make them smaller. So we want to make sure that our variables are on a relatively similar scale to begin with. And the way that we're going to do that here is by using the standard scalar. So I'm going to say z equals standard scalar, and then x train feat equals z dot fit transform x train feat, and then x test feat equals z dot transform x test feat. Okay, so feat, there we go. So when we do this, we should essentially have our z-scored variables. Let's just make sure that we do by saying x train dot head. Okay, so let's run this. Yep, okay, so now all of our variables are z-scored, which is very nice for us. Okay, so now that we have all of our z-scored variables, let's go ahead and build our models. So what I'm going to do is I'm going to build a regular regression model, a ridge regression model, and a lasso regression model, and we're just going to compare them a little bit. Now, in the future, and in class, we'll talk a little bit about how to choose that penalty harshness term. In the last lecture, we talked about lambda, which is essentially a measure of like how harsh do you want to be in the penalties for your regression coefficients. And the bigger lambda, the bigger your penalty. The smaller lambda, the less the size of the coefficients matters. We're going to talk about how to pick those in class, but for now, I just want to show you the syntax for how to create these models in general. So of course, you should remember for linear regression, we use the linear regression function. And we are going to say lr.fit x train y train. And then what I'm going to do is I'm going to print out the mean absolute error for both of these models. And so we can compare, or not both these models, for the train and the test data. So we can compare what is the mean absolute error in our training data versus our test data. Because remember, if there's a really big difference between those, that is to us a sign that maybe our model overfit a little bit. So I'm going to say print train. Okay, and then I'm going to say mean absolute error, and you could look at mean squared error or r squared, but I chose mean absolute error because it's sometimes mean absolute error is a little easier to understand because it's not like squared anything. So that's why I picked that. So I'm going to say y train, comma, lr.predict x train. Oh, and I want test. No, I want train first. Okay. So this is going to be the mean absolute error for our training data set. So this is data that we've already seen. And then we'll do the same for our test data set. So we'll say y test, and then we're going to have it predict based on the test values. So let's run that really quick. Okay, so we can see that our training mean absolute error is 0.292, whatever, about 0.3. And if you think about the IMDb ratings that we've seen, let's scroll up here, you can see they're probably on like a 10-point scale. So that's actually not bad. If the mean absolute error is about 0.3, that means that our ratings are typically off by 0.3. So it's not like super great, but we're, within a reasonable range. On our test set, however, our mean absolute error is about 0.4. So we can see that there is kind of a big difference between our training accuracy and our test accuracy, which indicates that it's possibly our model is overfitting to our data. Let's see what we can do with ridge regression next. I'm actually going to copy this because it's going to be really similar. So, well, let me just change all of these really quick first. Okay, so what we're going to be changing here is instead of linear regression, we're going to use the ridge function. And this is essentially going to fit a regression model, linear regression model, with a ridge penalty, which remember pushes small coefficients to be very, very small. It doesn't push them all the way to 0 necessarily, but it makes them very, very small. So let's see what happens when we run this. Cool. Okay. So we actually see not that huge of a difference in this case. So our training accuracy is again very similar to our the one from the normal linear regression. We can see that our test error is ever so slightly lower, but probably not meaningfully lower. So it looks like, at least in this data set, that ridge regression helped maybe a little bit, but actually not that much. Let's see what Lasso does. Okay, so with lasso regression, it's very similar to ridge. We're just going to use the lasso function. Oh, got rid of that extra parenthesis. I'm going to call this LSR. Cool. So when I run this, again, lasso pushes small coefficients to be exactly 0, and so we should see a little bit of a difference compared to ridge, but it's kind of a similar idea. Okay, interesting. So with Lasso, we actually see a higher error. However, we see a lot less difference between the training set and the test set error. And that's really good because in this case, at least, it indicates that our model is probably not overfitting as much as it was in the previous two models. So essentially, you can think about, well, okay, my error is a little bit higher in both of the sets. However, I'm willing to sacrifice a little bit of accuracy for the fact that my model will work on all data, not just my tiny little sample. So essentially, that's what you're looking for when you're doing ridge or lasso regression, is you want your model to be a little bit more generalizable. Okay, so those are the very basics. We'll talk a little bit about how to choose lambda, because when you do ridge and lasso regression, you can actually choose how harsh your penalty is, and we'll talk about that more in the lecture. But until then, I will see you next time.